In this module, we're going to talk about the common ion effect and its role in solubility. So let's look at a solution of magnesium, that we make by dissolving some magnesium carbonate in water at 25 Celsius, of course. This is the equilibrium, and this is the KSP. So, just like before, we can calculate the solubility of magnesium carbonate, and we get about 2.6 times 10 to the minus 3 moles per liter. Now, let's look what happens when we add a common ion, that is magnesium, in the form of magnesium nitrate. Then now, see, the nitrate doesn't matter. It does not precipitate with anything. It's not involved in any of the chemistry in the solution. It's just there so we can get the magnesium ion into solution. And let's say we have 0.0500 molar magnesium nitrate. When we add that to the solution, it's the magnesium that we care about. So now, if we look at this equilibrium, where the initial concentration of magnesium is 0.05, which came from this magnesium nitrate, everything else, 0 like here, we do our ice table, same KSP, and we get that the solubility is about 1.4 times 10 to the minus 4th moles per liter. Notice I neglected S compared to 0.05, and yes, that was a good approximation because 1.4 times 10 to the minus 4th is a lot less than 5% of 0.05. Anyway, so comparing the solubility now with the magnesium nitrate in there, the 0.05 molar, to what it was before, it's less. It's about an order of magnitude less. So we decrease the solubility. And you can see that just thinking about Le Chatelier's principle too. If we add something over here, the equilibrium shifts to the left. Now let's look at what happens when we adjust the pH of a solution. This is only going to affect the solubility of a salt if that salt contains either hydroxide or the conjugate base of a weak acid. And I'll show you that one in just a second. But let's look at strontium hydroxide. Strontium hydroxide certainly contains hydroxide, and so and its KSP and it ends up is like 3.2 times 10 to the minus 4th. If we calculate the solubility just like we've been doing, we get the solubility is 0.043 molar, and that gives us, and the solubility, 2 times the solubility will be the concentration of hydroxide. So if we take the negative log base 10 of that, and we get the pOH, 1.06, which means the pH, 14 minus the pOH, is 12.94. Okay, so what that tells us is that if we adjust the pH of this solution so that the pH is higher than 12.94, we make it more basic, we're going to shift the equilibrium back to the left, and we're going to decrease the solubility of the strontium hydroxide. On the other hand, if we acidify the solution, lower the pH lower than 12.94, then the excess hydrogen ions will react with the hydroxide, pulling them out, making water, shifting the equilibrium to the right, increasing the solubility of the strontium hydroxide. Now, let's look at a salt that contains the conjugate base of a weak acid, calcium fluoride. So fluoride is the conjugate base of hydrofluoric acid. Hydrofluoric acid is a weak acid. And so if we have the solution that we've made by dissolving some calcium fluoride in there, in water, there's a KSP. And if we were to acidify that solution, the hydrogen ions would react with the fluoride, pulling it out, making hydrofluoric acid and shifting the equilibrium this way. Now the K for this reaction is just 1 over Ka for hydrofluoric acid. It ends up Ka for hydrofluoric acid is 7.2 times 10 to the minus 4th. 1 over that is about 1.4 times 10 to the 3rd. 1,400. That's pretty big, which means equilibrium-wise far on this side. So we're pulling a lot of this fluoride out, most of it out, really helping dissolve that calcium fluoride.